Radar operators froze as an enormous shadow swept across the frozen steppe. The blip on their screens was moving, but nothing that size should have been able to hover. NATO reconnaissance stations along the Soviet border had been tracking aircraft for years, cataloging every movement, every new design that emerged from behind the Iron Curtain. But this was different. The acoustic signature was thunderous, a deep rhythmic pounding that registered on seismic sensors kilometers away. When the shape finally broke through the low clouds, rising above the tree line with a rotor wash that flattened everything beneath it, the observers reached for their cameras with trembling hands. What they photographed that morning in 1977 would fundamentally alter Western assessments of Soviet military capability and force a complete re-evaluation of what was physically possible in aviation engineering. The photographs arrived at NATO headquarters in Brussels, marked with the highest classification levels. Intelligence analysts gathered in secure briefing rooms, studying images that showed something that appeared to defy the laws of physics. A helicopter with a main rotor diameter exceeding 32 meters, larger than the wingspan of many fighter jets. A fuselage stretching nearly 40 meters from nose to tail, comparable in length to a Boeing 737. Initial calculations suggested a maximum takeoff weight approaching 56,000 kilograms and an internal cargo capacity that dwarfed anything the West had developed or even conceived. The numbers were checked and rechecked. Aviation engineers were consulted, their expertise sought to determine whether what the photographs showed could actually exist. Every analysis confirmed the same impossible conclusion. The Soviet Union had built a helicopter so massive that Western experts had previously dismissed such a design as theoretically unworkable, and somehow, impossibly, they had made it fly. The machine in those grainy reconnaissance photographs represented the culmination of Soviet ambition in an era defined by technological competition between superpowers. The Cold War had evolved beyond nuclear arsenals and missile counts into a broader struggle for supremacy across every dimension of military capability. Tanks, submarines, aircraft, satellites, each domain became an arena where East and West sought to demonstrate superior engineering and operational capability. But logistics had always been the great constraint on military power. Armies needed supplies, equipment needed to reach forward positions, casualties needed evacuation. The side that could move more material faster and farther would hold decisive advantage in any conflict. The Soviet Union understood this arithmetic of warfare better than most, having experienced the brutal lessons of the Second World War, where logistics often determined outcomes as much as tactics or courage. The Soviet Union faced unique logistical challenges that Western militaries never confronted at comparable scale. The vast territory stretching from Eastern Europe across 11 time zones to the Pacific included enormous regions with virtually no infrastructure. Siberian tundra, where temperatures dropped to -50 degrees. Arctic wastelands where permafrost prevented conventional construction. Mountain ranges that isolated entire regions for months each year. Desert expanses where heat and distance defeated conventional transport. Roads were sparse or non-existent across vast swaths of territory. Railways served major corridors between cities and industrial centers, but couldn't reach remote military installations or rapidly shifting forward deployments. Fixed-wing cargo aircraft could carry substantial loads, but required prepared runways, and building airfields across the Soviet interior was prohibitively expensive and time-consuming, requiring months or years of construction that tactical situations rarely allowed. Helicopters offered the solution to these geographic and logistical constraints. They could land anywhere with sufficient open space, operate from unprepared sites with minimal ground support, deliver equipment directly to where it was needed without intermediate infrastructure or transshipment, But existing helicopters, even the largest Soviet designs, were limited in what they could carry and how far they could transport it. The Mi-6, introduced in the 1950s and at the time the world's largest helicopter, could carry 12 tons of cargo or deploy infantry squads with their equipment across distances of several hundred kilometers. For many missions, this was adequate, but Soviet military planners and industrial designers envisioned operations requiring capabilities that exceeded what the Mi-6 could provide. They imagined scenarios where armored personnel carriers or light tanks needed rapid deployment to contested regions without road access. They envisioned artillery batteries being positioned on mountain ridges or in valley positions that ground vehicles couldn't reach. They planned for the construction of remote radar stations or missile sites requiring heavy equipment and prefabricated structures to be delivered to locations hundreds of kilometers from the nearest road. They anticipated disaster response scenarios where entire field hospitals with surgical equipment and supplies would need deployment to earthquake zones or industrial accident sites. All of these missions required a helicopter that could carry not 12 tons, but 20 tons or more, effectively doubling the capability of the best existing designs while maintaining reliability and operational range. The specifications seemed impossible given the engineering challenges involved, but in the Soviet system, impossibility was merely a challenge to be overcome through determination and willingness to accept whatever costs and complexities the solution demanded. The Mil-Moscow helicopter plant, named for legendary designer Mikhail Mil, who had revolutionized Soviet helicopter development and created the Mi-6 that established Soviet dominance in heavy-lift rotary wing aircraft, received the assignment to develop this unprecedented machine. Mil himself had died in 1970, his legacy already secure as one of the great aviation designers of the 20th century. But the design bureau he founded remained the heart of Soviet helicopter development, staffed by engineers who had worked under Mil and absorbed his design philosophy. Chief designer Marat Tishchenko, who had collaborated with Mil on previous projects, assembled a team of specialists across multiple disciplines to tackle what would become one of the most ambitious aviation projects of the Cold War era. Aerodynamicists would design rotor blades that could generate unprecedented lift. Structural engineers would create a fuselage strong enough to carry massive loads without excessive weight. Propulsion specialists would develop engines powerful enough to lift the entire assembly. Systems engineers would integrate everything into a functional aircraft that pilots could actually fly. The project designation was V-12 initially, a number that carried no particular significance beyond sequential assignment in the Bureau's design registry. Later, it would be changed to Mi-26 when it entered military nomenclature and production planning. The challenge facing Tishchenko's team was straightforward to articulate but extraordinarily difficult to solve. Build a helicopter with double the lifting capacity of the Mi-6, the previous record holder and largest operational helicopter in the world, while maintaining reliability, operational practicality, and performance characteristics that would make it genuinely useful rather than merely impressive as a technology demonstrator. The aircraft would need to operate in temperatures ranging from Arctic cold to desert heat. It would need to function at altitudes from sea level to mountain elevations exceeding 4,000 meters. It would need to be maintainable by military technicians under field conditions without elaborate facilities or specialized equipment. And it would need to be producible in meaningful numbers, not as a handful of experimental prototypes, but as a production aircraft that could equip aviation regiments across the Soviet military. The engineering obstacles were formidable and deeply interconnected. Lifting capacity in a helicopter is determined primarily by rotor diameter and engine power, but simply scaling up existing designs proportionally would create insurmountable problems. Larger rotors generate more lift through increased disk area, but they also generate proportionally more drag and impose dramatically greater structural stresses on the rotor head and transmission system. The rotor blades would need to be incredibly strong to resist the centrifugal forces and aerodynamic loads they would experience, yet light enough that their weight didn't overwhelm the engines. The engines themselves would need to produce power levels far beyond anything previously installed in helicopters, yet remain reliable enough for military service. The transmission connecting engines to rotor would have to handle torque loads that would destroy conventional helicopter drivetrains within minutes of operation. The fuselage would need to accommodate cargo volumes and weights that exceeded what any helicopter had been designed to carry, with structural strength to prevent catastrophic failure under maximum load conditions. Every system would be pushed to absolute limits, operating at the edge of what materials, science, and engineering knowledge could achieve in the 1970s. The solution required fundamental innovation across virtually every aspect of the design rather than incremental improvements to existing technology. The main rotor would use 8 blades, rather than the 5 or 6 typical of large helicopters, distributing lift more evenly across the rotor disc and reducing stress concentrations on individual blades. Each blade would be over 16 meters long, constructed from titanium spars that provided exceptional strength-to-weight ratio, wrapped in composite materials that protected the structure while minimizing aerodynamic drag. The rotor diameter of 32 meters created a disk area of over 800 square meters, larger than the wing area of many commercial aircraft. The rotor head, the complex mechanical assembly connecting blades to the rotor shaft and allowing them to articulate through their range of motion, would be a masterpiece of precision engineering. It used advanced bearings capable of handling the enormous loads, sophisticated articulation systems that allowed each blade to adjust its pitch and angle independently, and damping systems that absorbed vibrations before they could propagate into the airframe. The engines were purpose-designed specifically for the Mi-26 through collaboration between the Mil Design Bureau and the Evchenko Design Bureau in Ukraine, which specialized in turboshaft engines for helicopters. The result was the D-136, which would become the most powerful helicopter engine ever created and would remain so for decades. Each unit produced 11,400 shaft horsepower at maximum rating, more power than many ships' engines and sufficient to drive industrial equipment or generate electricity for a small town. The Mi-26 would mount 2 D-136 engines in nacelles on the fuselage top, positioned to balance weight and provide redundancy while keeping the engines accessible for maintenance. The combined output of 22,800 horsepower exceeded the total installed power of entire bomber formations from the Second World War. The engines featured advanced multi-stage axial compressors that compressed intake air to high pressures, sophisticated combustion chambers that burned fuel efficiently even at varying altitudes and temperatures, and carefully designed turbine sections that extracted maximum energy from the hot exhaust gases. Cooling systems used air ducted through internal passages to prevent critical components from overheating. Exhaust design directed hot gases upward and away from the helicopter to prevent recirculation into the air intakes or interference with the rotor downwash. Connecting that massive engine power to the rotor required a transmission system that was itself a marvel of mechanical engineering and represented decades of accumulated Soviet experience in heavy machinery design. The main gearbox weighed over 3,000 kilograms, a mass comparable to a small automobile, yet it had to function with extreme reliability under conditions that would destroy lesser designs. The gearbox used a complex arrangement of reduction gears, each one precision machined to tolerances measured in fractions of millimeters, to convert the high-speed rotation of the engine turbines into the much slower rotation of the main rotor. The engines turned at speeds exceeding 10,000 revolutions per minute, while the main rotor turned at approximately 200 revolutions per minute, requiring a reduction ratio of roughly 50-1. The gearbox had to handle continuous torque loads that would twist conventional shafts into pretzels while maintaining precise synchronization between the two engines and absorbing the dynamic loads created by the rotor during flight maneuvers. Lubrication systems used high-pressure pumps to ensure oil reached every bearing surface and gear mesh, and temperature sensors monitored for any sign of overheating that could indicate impending failure. The transmission represented the culmination of Soviet expertise in heavy machinery, applying principles learned from industrial equipment, marine propulsion, and previous helicopter designs to create a system that could reliably transfer unprecedented power levels. The fuselage was designed as a flying cargo container optimized for military logistics operations. The internal cabin measured 12 meters in length, more than 3 meters in width, and over 3 meters in height from floor to ceiling, creating a usable cargo volume of 120 cubic meters. To provide context, this was sufficient space to accommodate 2 standard shipping containers or an entire infantry platoon with full equipment. The floor was reinforced with titanium and high-strength steel alloys to handle concentrated loads from wheeled or tracked vehicles without collapsing or deforming. A rear loading ramp, hydraulically operated and capable of being lowered in flight or on the ground, could be opened to allow vehicles to drive directly aboard or cargo to be rolled in on pallets using motorized winches. The ramp design included a sophisticated hinge system that maintained structural integrity of the fuselage while providing a large opening for oversized cargo. Internal tie-down points welded throughout the cargo bay allowed loads to be secured against the accelerations and vibrations of flight. The cabin was unpressurized, keeping the design simpler and lighter, but environmental control systems maintained temperature and ventilation adequate for crew and passengers. The first prototype emerged from the mill facility in late 1977, a machine so large that it dominated the hangar and test facility where it was assembled. Workers who had spent years building helicopters found themselves awed by the sheer scale of what they had created. The maiden flight occurred on December 14, 1977, with test pilot B.A. Galitsky at the controls, accompanied by a flight engineer and test observer. The takeoff was cautious, a brief hover to confirm basic flight characteristics, verify that control inputs produced expected responses, and ensure that no critical systems were failing under actual flight loads. After just a few minutes in the air, Galitsky landed the prototype, and engineers immediately began detailed inspections to verify that everything had functioned as designed. But those few minutes confirmed what the calculations and wind tunnel tests had predicted. The Mi-26 flew. It was stable. The rotor generated sufficient lift with acceptable efficiency. The engines provided adequate power with reasonable fuel consumption. The transmission functioned without catastrophic failure or dangerous vibration levels. The control systems responded predictably to pilot inputs. Over the following months and years, the test program gradually expanded, each flight pushing a little further, testing new aspects of the flight envelope, demonstrating capabilities that seemed impossible for a machine of this size. Test pilots explored the speed range, eventually confirming that the Mi-26 could cruise at 255 kilometers per hour, faster than many smaller helicopters. They tested high-altitude performance, climbing to altitudes exceeding 4,500 meters, even with substantial cargo loads. They evaluated handling qualities with various cargo configurations, learning how the helicopter behaved with the center of gravity shifted by different load distributions. They tested maximum lift capacity by progressively loading heavier external cargo on the belly hook, eventually confirming that the Mi-26 could lift approximately 20 tons and maintain controlled flight. During one dramatic test, engineers loaded a retired T-55 tank weighing approximately 36 tons onto the cargo hook to test absolute maximum lift capacity. The helicopter lifted the tank, demonstrating that its actual capability exceeded design specifications by a substantial margin. NATO intelligence detected the test program through multiple overlapping channels that the Soviet Union could not completely conceal despite extensive security measures. Signals intelligence stations monitored communications between test pilots and ground controllers, analyzing the technical language for clues about performance characteristics. Reconnaissance satellites photographed the helicopter during ground tests and flight operations, capturing images that revealed size and configuration details. Human intelligence sources, agents, and informants within Soviet industrial facilities or military organizations provided fragmentary reports about a massive new helicopter under development at the mill plant. The pieces came together slowly into a picture that Western analysts found deeply troubling. The Soviet Union had successfully developed a helicopter with capabilities far exceeding anything in Western inventories or even in Western development programs, and it was moving rapidly toward operational deployment rather than remaining an experimental prototype. The designation NATO assigned was HALO, following the alliance tradition of using reporting names beginning with H for Soviet helicopters, a system that made verbal communication and written reports clearer by avoiding confusion with model numbers or designations. But the name carried implications and associations beyond simple identification convenience. A halo suggests something divine or transcendent, something beyond ordinary mortal capability, and that's exactly what the Mi-26 represented to Western observers who understood its capabilities and their strategic implications. It was a helicopter that transcended previous understanding of what such aircraft could achieve, a machine that forced a fundamental reassessment of Soviet engineering capability and raised uncomfortable questions about whether Western militaries had become complacent in their assumptions about technological superiority. Production began in 1980 at the Rostov Helicopter Production Complex, a massive facility in southern Russia that had been expanded specifically to accommodate Mi-26 manufacturing, and the first operational Mi-26 helicopters entered Soviet military service in 1983 after completing military acceptance trials. The initial production run equipped Soviet Army aviation units stationed in the European theater, where they would face NATO forces in any conflict, and in Central Asia, where ongoing military operations in Afghanistan demanded maximum logistical capability under the most challenging conditions imaginable. Soviet forces discovered immediately that the Mi-26 transformed operational possibilities in ways that smaller helicopters simply couldn't match, and that had profound implications for military planning. Equipment that previously required multiple sorties by several helicopters, creating vulnerable patterns that enemy forces could predict and target, could now be delivered in a single Mi-26 flight. Artillery pieces could be positioned on mountain ridges or hilltops that provided commanding fields of fire but were completely inaccessible by road. Armored personnel carriers could be deployed to remote valleys or forward positions without warning, achieving tactical surprise that ground movement could never accomplish. Construction equipment for building fortified positions could be delivered complete with operators and materials in a single lift. The Afghanistan War provided the Mi-26 with its combat debut and proved the value of the design under the most demanding operational conditions imaginable. Soviet forces found themselves fighting across some of the world's most difficult terrain, mountain ranges where roads were non-existent or easily blocked, valleys that could only be reached through narrow passes that were perfect ambush sites, and high-altitude plateaus where thin air reduced helicopter performance dramatically. The Mi-26 became the logistics backbone for operations in regions where other forms of transport simply couldn't function effectively or couldn't deliver the quantities of supplies that forward positions required. It delivered construction equipment, including bulldozers and concrete mixers, to build fortified positions on strategic hilltops. It transported artillery pieces, including 122mm howitzers, complete with ammunition supplies sufficient for extended operations. It evacuated damaged helicopters by lifting them as external loads using the cargo hook, rather than abandoning expensive equipment that insurgents could capture and exploit for propaganda. It conducted mass casualty evacuations, fitting over 80 wounded soldiers in its cargo bay with medical attendants for rapid transport to field hospitals hundreds of kilometers away. Afghan Mujahideen fighters learned to fear and respect the distinctive sound of the Mi-26's rotor, the deep, rhythmic thunder that announced incoming Soviet supplies or reinforcements that could rapidly shift tactical situations that had seemed favorable just minutes before. But the Mi-26's most famous mission, the operation that would define its public image for decades and demonstrate its value beyond military applications, came not in combat, but in the aftermath of the Chernobyl nuclear disaster that shocked the world. When Reactor 4 at the Chernobyl nuclear power plant exploded catastrophically on April 26, 1986, releasing unprecedented quantities of radioactive material into the atmosphere in what would become the worst nuclear accident in history, Soviet authorities faced a crisis that had no precedent and no established response procedures. The exposed reactor core was literally on fire, the graphite moderator burning and releasing radioactive smoke and particles that were spreading contamination across vast areas. Radiation levels near the destroyed reactor were so intense that ground operations were impossible without exposure doses that would be immediately fatal or cause death within days. The immediate priority, recognized by nuclear physicists and emergency planners, was to smother the graphite fire and contain the radiation release by dropping massive quantities of shielding material onto the shattered reactor from above. Mi-26 helicopters were deployed to Chernobyl alongside smaller Mi-8 helicopters for what would become one of the most dangerous aviation missions ever attempted by any military or civilian organization. Helicopter crews would be required to fly directly over the destroyed reactor, maintaining precise hover positions while loads of sand, lead, clay, and boron compounds were manually released through cargo doors by crew chiefs leaning out of the aircraft, all while being exposed to radiation levels that were lethal with prolonged exposure and could cause serious harm even in the minutes required for each drop. The Mi-26's advantages were absolutely critical for this mission and probably made the difference between partial success and complete failure. Its large cargo capacity allowed delivery of much larger loads per flight, reducing the total number of flights required and thus reducing cumulative radiation exposure for crews. Its powerful engines permitted hovering at higher altitudes above the reactor, slightly reducing radiation intensity through increased distance from the source. Its spacious cargo bay could be loaded and unloaded quickly at staging areas away from the contamination zone, minimizing time that ground crews spent near radioactive materials. Over several harrowing days in early May 1986, helicopter crews flew mission after mission, more than 100 sorties in total, dropping approximately 5,000 tons of material onto the burning reactor in a desperate attempt to smother the fire and reduce the radiation release that was contaminating enormous areas and threatening millions of people. The pilots and crew chiefs received radiation doses that far exceeded any safe limits, exposure that would have long-term health consequences for many of them, but their actions successfully smothered the graphite fire and dramatically reduced the immediate radiation release that was the most urgent threat. The helicopters themselves became contaminated with radioactive particles, requiring extensive decontamination procedures after each mission, and some aircraft absorbed so much radiation that they had to be permanently retired rather than risk exposing maintenance crews to dangerous contamination. The mission demonstrated conclusively that the Mi-26 wasn't merely a military transport optimized for logistics support, but a critical national asset capable of responding to disasters that no other aircraft could address effectively, establishing its value beyond any purely military calculation. The collapse of the Soviet Union in 1991 created profound uncertainty about the future of many Soviet military systems, but it didn't end the Mi-26's operational career or relegate it to museums as a relic of a vanished empire. The helicopter entered service with the air forces of multiple former Soviet republics, including Ukraine, which hosted the Ivchenko Design Bureau that built the engines, and Belarus, which had mill production facilities, along with Russia itself, which inherited the bulk of Soviet military aviation assets. The Mi-26 was also exported to countries seeking heavy lift capability that no Western helicopter could match, including India, which used them for operations in the Himalayas, and several African nations that needed them for operations in regions with no infrastructure. Russia continued operating Mi-26 helicopters in both military and civilian roles throughout the turbulent 1990s and into the new century, finding that despite economic difficulties and budget constraints, the Mi-26's unique capabilities justified maintaining the fleet. During the Chechen conflicts of the 1990s and 2000s, Mi-26 helicopters provided crucial logistics support for Russian forces operating in the Caucasus Mountains, where ground supply routes were extremely vulnerable to ambush and interdiction, delivering supplies and evacuating casualties under conditions that made ground transport nearly impossible. The Russian Ministry of Emergency Situations, the government agency responsible for disaster response and civil defense, adopted Mi-26 helicopters as a critical component of their response capabilities, using them for firefighting operations where they could deliver enormous quantities of water or fire retardant to remote forest fires, and for delivering relief supplies to areas affected by floods, earthquakes, or industrial accidents where ground access was disrupted. International recognition of the Mi-26's unique capabilities led to its use by organizations worldwide that needed heavy lift capability beyond what any alternative could provide. The United Nations chartered Mi-26 helicopters operated by Russian crews for peacekeeping and humanitarian operations in Africa and Asia, using them to deliver supplies and equipment to regions with absolutely no infrastructure, where roads didn't exist and runways couldn't be built in the time frames that emergency situations demanded. Commercial operators purchased Mi-26 helicopters for heavy lift operations, supporting construction projects that required moving equipment to remote sites, oil and gas exploration in Arctic and subarctic regions where ground transport was impossible for much of the year, and mining operations in mountainous terrain where the only alternative was building roads that would cost tens of millions of dollars and require years to complete. Western militaries watched the Mi-26's continued operations over the decades with persistent interest tinged with a degree of frustration that their own industries had never produced anything comparable. The United States explored developing comparable heavy-lift helicopters multiple times in the years and decades following the Mi-26's introduction, conducting feasibility studies and preliminary design work, but never committed to actual development and production. American military doctrine emphasized different capabilities, including speed and survivability, rather than absolute lifting capacity, and the enormous development costs, combined with relatively limited anticipated demand compared to other priorities, made such a program difficult to justify when budgets were constrained. European nations operated capable heavy-lift helicopters, including various models that could carry impressive loads, but nothing approaching the Mi-26's sheer capacity or cargo volume. China eventually developed indigenous heavy-lift helicopter designs through its own aviation industry, benefiting from access to Mi-26 technology through purchases and industrial cooperation, creating aircraft that borrowed heavily from Soviet design principles. But decades after its first flight, approaching half a century of service, the Mi-26 remained the largest and most powerful helicopter in operational service anywhere in the world, a record it continues to hold into the present day, with no clear challenger on the horizon. The specifications that had seemed impossible when NATO analysts first studied those reconnaissance photographs in the winter of 1977 remained unmatched well into the 21st century. Maximum takeoff weight of 56,000 kilograms, heavier than many fixed-wing transport aircraft. Internal cargo capacity of 20,000 kilograms carried in the pressurized cargo bay. External load capacity of 20,000 kilograms suspended beneath the fuselage on cargo hooks. Cargo bay volume of 120 cubic meters, sufficient for 2 shipping containers or light vehicles. Cruise speed of 255 kilometers per hour, faster than most heavy-lift helicopters. Service ceiling of 4,600 meters, even when fully loaded, allowing operations in high-altitude regions. Ferry range exceeding 800 kilometers with maximum internal fuel. These numbers represented not merely engineering achievement or technical specifications to be compared in reference books, but a fundamental philosophy of design that prioritized absolute capability over cost considerations or efficiency metrics. The Soviets had built the Mi-26 not because it was economical or practical by Western cost-benefit analysis standards, but because they believed that possessing the world's largest and most capable helicopter was strategically valuable in itself, that the psychological impact and operational flexibility it provided justified whatever resources its development and production consumed. The machine's symbolism extended well beyond its technical specifications into the broader realm of Cold War perception, prestige, and the competition for technological supremacy that defined the era. The Mi-26 represented Soviet engineering ambition at its apex, the crystallization of a belief system that held technical challenges could be overcome through determination, through willingness to accept complexity and expense that Western nations might reject, through commitment to achieving maximum capability regardless of conventional wisdom about practical limits. Western helicopter designers and military planners had concluded, based on extensive analysis and experience, that helicopters beyond a certain size became impractical, that engineering challenges and operational costs outweighed whatever benefits increased capacity might provide. Soviet designers rejected those conclusions entirely, proving through the Mi-26 that significantly larger helicopters were not only possible but operationally valuable across a wide range of missions. The Mi-26 stood as a powerful rebuke to Western assumptions about technological limits. a demonstration that Soviet engineering could produce systems that the West either couldn't match or had decided weren't worth attempting. The sound of a Mi-26 in flight remains distinctive and utterly unforgettable to anyone who has experienced it directly. The eight-blade rotor creates a deep, resonant thunder quite unlike the characteristic rhythmic chop of smaller helicopters with their four- or five-blade rotors. The rotor downwash is powerful enough to flatten vegetation across wide areas, kick up dust storms that reduce visibility to near zero, and generate pressure waves that can be felt hundreds of meters away from the aircraft. When an Mi-26 approaches a landing zone or operating area, you hear it long before you see it, a growing thunder that builds in intensity as the massive machine draws nearer, a sound that penetrates buildings and drowns out conversation. When it passes directly overhead, you feel the rotor wash, pushing down with almost physical force, a wind that makes standing difficult, and you understand in a visceral, immediate way what the term heavy-lift helicopter truly means beyond any abstract specification or weight figure. Today, decades after that first flight, Mi-26 helicopters continue flying across continents and mission profiles. Production ended temporarily in the early 1990s as the Soviet Union collapsed and Russian aviation industry struggled with economic chaos, but it resumed in the 2000s with modernized variants featuring upgraded avionics that replaced Soviet-era analog instruments with digital displays, more efficient engines with improved specific fuel consumption, and enhanced systems incorporating decades of operational experience and technological advancement. Approximately 300 Mi-26 helicopters have been built since the first prototype emerged from the mill facility, serving with military forces and civilian operators in over 20 countries across Europe, Asia, Africa, and South America. Some helicopters, built in the early 1980s, remain operational after 4 decades of continuous service, testament to robust Soviet engineering that prioritized durability and maintainability, combined with continued maintenance programs that keep the aging fleet airworthy. The helicopter that NATO analysts first observed in grainy satellite photographs nearly 50 years ago remains the largest and most capable helicopter in operational service anywhere in the world, a record that appears unlikely to be challenged in any foreseeable future, as no nation has announced serious programs to develop anything larger. The legacy of the Mi-26 extends well beyond its continued operation as a working aircraft into its broader influence on helicopter technology development and military thinking about logistics and air mobility. It proved definitively that helicopter technology could be pushed far beyond what Western engineers believed possible based on their experience and analysis, establishing a capability benchmark that has never been exceeded and may never be exceeded as the emphasis in modern helicopter development has shifted toward speed, efficiency, and specialized capabilities rather than absolute lifting capacity. It demonstrated Soviet willingness and ability to commit to creating maximum capability systems, regardless of cost or complexity, when leadership determined such systems served strategic purposes or enhanced national prestige. It provided logistics capabilities that gave Soviet and later Russian forces significant advantages in specific operational scenarios where helicopter transport was the only practical option and where no alternative existed. And it stands as perhaps the single most tangible symbol of Cold War technological competition in the aviation domain. A machine born from the drive to surpass a rival and prove superiority through concrete engineering achievement that could be measured and compared. They called it Halo, a monster that shouldn't have been able to fly, a flying fortress that redrew the boundaries of what helicopters could be, an impossible machine that existed despite every rational analysis suggesting it was impractical. The engineers who designed it pushed every system to unprecedented scales, creating a helicopter that fundamentally redefined rotary wing aviation and established capabilities that have never been matched. The crews who flew it proved its worth across combat zones, disaster sites, and peacekeeping missions on multiple continents, demonstrating that the theoretical capabilities on paper translated to genuine operational utility. The intelligence analysts who first discovered it through satellite reconnaissance recognized immediately that the Soviet Union had built something genuinely remarkable, a logistics weapon that no Western nation had matched or seriously attempted to match in the decades since, despite having ample opportunity and resources to do so if they had chosen that path. The Mi-26 remains precisely what it was from its first tentative hover in that winter of 1977, the largest helicopter ever built, the most capable heavy-lift rotorcraft in operational service, a testament to the ambition of an empire that sought to prove its greatness through engineering prowess as much as through military might or ideological conviction. The thunder of its eight-bladed rotor still echoes across mountains and tundra and deserts, carrying loads that still seem impossible when you see them suspended beneath that massive fuselage, flown by crews who operate a machine that broke every conventional rule about what helicopters could be and what missions they could accomplish. It was born in secrecy behind the Iron Curtain, revealed through patient intelligence work and satellite reconnaissance, and became legend through sheer capability demonstrated across decades of operations. The giant that terrified NATO by simply existing, by proving that Soviet engineering could achieve what Western experts believed impossible, and that decades later still flies, still lifts, still proves that sometimes the impossible is simply what no one else was willing to attempt or commit the resources to achieve. The rotor blades still turn, cutting through the air above distant landscapes, carrying the weight of history and the legacy of an era when two superpowers competed to build machines that would define the limits of human technological achievement and demonstrate supremacy through engineering as much as through weapons. And in that sound, that deep rhythmic thunder that announces the Mi-26's approach from kilometers away, there remains an echo of the Cold War itself, the age when nations measured their worth in tons lifted and records broken, and capabilities that left adversaries in awe, when engineering was a battlefield where victories were measured in specifications and performances that rewrote what was considered possible. The halo flies, still, a monument in motion to an era that has passed, but whose legacy remains visible every time those massive rotors turn and that impossible machine takes to the sky, defying gravity and expectations in equal measure, carrying the banner of an empire that no longer exists, but whose engineering achievements continue to cast long shadows across the world of aviation.